Good evening and welcome to the live session. It is 6 p.m., but till now only Mr. Buragada has joined. So we'll wait for a few more minutes before we start. Thank you. Good evening and welcome to week 6 of the live sessions for Fundamentals of Additive Manufacturing Technologies. This course is taught by Professor Sajal Kapil, who's a faculty member in the Department of Mechanical Engineering at IIT Guwahati, and I am Sourav Goswami. I'm a PhD candidate in the Department of Mechanical Engineering at IIT Bombay. Last week, we finished talking about liquid-based additive manufacturing processes. That is all processes that used liquid as their raw feedstock material. And this week, the lectures covered sheet-based additive manufacturing processes, or those processes which used sheets as their raw feedstock. Some of these technologies were cubic technologies, laminated object manufacturing or LOM, Kira's paper lamination technology, Solid Dimensions plastic sheet lamination, CAMLAM, and NX Corporation's offset fibers. Again, we have this very helpful subsystem-based classification of the processes. So first, for cubic technologies norm, we see that it uses paper, sheets of paper as the raw feedstock material, and uses a bond and then form strategy. We'll talk about both the strategies in a minute. Bond then form and form then bond. For cutting, it uses a laser. The bonding method is via adhesive between the paper sheets, and the entire sheet of paper under one section is joined. Now, very interestingly, despite it being an additive process, what we can see here is this cutting method subsystem, which is very counterintuitive because, by definition, additive manufacturing processes are those which do not really have a conventional subtractive or formative step. But if you would remember from our very first sessions, you mentioned how all sheet-based additive manufacturing processes are of a hybrid nature. And this is because just by joining sheets, what you will end up with is a cubical or cuboidal type of geometry. Say you keep on stacking sheets one after the other. But to actually end up with some part inside, say, like a sphere or so, you will actually have to get rid of all of this excess material around. And that requires a subtractive step. So the nature of all sheet-based additive processes is such that it requires one or in some cases more subtractive steps. Thus, they are of a hybrid nature. Now, the two approaches to uh, bond these sheets together. In the first approach, which is form and then bond, we cut out the desired shape from the sheet. So this is our sheet of raw material, say paper. And when we are building this star-like object, we first cut out the outline of the star or the contour of the star. So from each layer, and then we bond it to the previously deposited. So if this was n plus 1th layer, this is the star cut out from the nth layer. However, this presents its own difficulties. Handling the cut pieces can often be a challenging task because, more often than not, they will not be of a simple regular geometry. Again, each slice may have multiple such contours. It's not necessary that you will only end up with one contour, say. You also have some smaller star here, or a round object here, maybe a square here, and so on, some arbitrary shape at the side. And thus, you will have to account for all of these contours that you cut out from the same slide. Handling them is not easy, they are not of a uniform cross section. Such pieces may be odd shaped, as we already saw. And then in certain cases where raw material such as paper is used, they are not really very rigid and they are of flexible nature. Thus, handling paper or paper-like substances becomes even more challenging because it will flail around, it will not remain rigidly clamped. And a support mechanism may be required, which we can see that there is no provision for any supports in this form and then bond process. Say for this n plus 1th layer, you had a star of a similar shape, but for the n plus 2th layer, say you have like a larger star. Now you want to superimpose this onto this previously bonded layers. But if I just draw a rough contour of the previous already deposited structure, maybe something like this. You see that all of this extra region over here, the region that is highlighted in green, all of this is unsupported. Now, if this were a metal sheet or a ceramic sheet, there is still a chance that it might have sustained by itself. But in the cases of raw materials like paper, this is a very high chance that all of these arms will simply droop down under the action of gravity and they will remain unsupported. On the other hand, if you use a bond and then form approach, that is, say you have a previously deposited structure, you have been depositing this for some time, say these are the layers, and to the nth layer, now you're adding this n plus 1th layer. We first bond it together via a suitable bonding mechanism such as a regular adhesive such as glue or a thermally activated glue or resin or some other means. And then once it is attached, you then form this contour that you have to machine out from this specific layer. And additionally, you must also scan what are called these grid lines for decubing, which allows for easier removal later on. We'll talk about this in details. And one thing you can easily notice is that in this case, the machining operation must be very precise. In the previous case here, say you might have some sacrificial plate at the bottom, and thus you could be a little lenient with your machining in terms of the depth of machining that you want to achieve. So even if you cut a little deeper than you intended, it's okay because there is only some sacrificial plate at the bottom. Whereas in this case, there's already a previously deposited layer here and some region which must have been scanned on that layer. And so for this new n plus 1th layer that you are now depositing, if you were to cut deeper than the intended depth, which nominally is equal to the depth of the or thickness of the sheet itself, you will end up damaging the previously deposited layer, which is highly undesirable. So in this case, the machining must be more precise, and we must exercise greater control over the machining aspect, specifically and especially the depth of cut. Some other aspects. So handling is easier because again you are just pasting it to the already deposited structure and then cutting. Indexing of the reel is all that is required. So typically you will have these rollers, either one or two, which send the sheet. So maybe and then take up the sheet as well on the other side. You index it by a fixed distance for each pass. The remaining stock acts as a support material. That is all this region which we have marked grid lines on, which will be later removed via the decubing process. For the time period now, they are acting as the support structures. So no additional or explicit supports are needed. Drawback comes in terms of the production times. The decubing operation is perhaps the rate determining step or the slowest step. Additionally, you also have uh, you must account for time that is required for this decubing or grid cutting operations. and it is especially suitable for paper-like flexible materials which cannot support their own weight or which flail under the act of gravity. So laminated object manufacturing, I'll just write it here. Often this is also one of the terms which is commonly used in the context of or in the general context of any sheet-based additive manufacturing process. Is an automated fabrication method in which 3D objects are constructed from a solid CAD representation by sequentially laminating the part cross section. So, general additive manufacturing definition. And it has your regular three phases: pre-processing, the build process, and for the post-processing. Again, just like any other AM process, we'll start from the CAD file, convert it to STL if we are resorting to indirect slicing. If we resort to direct slicing, this intermediate conversion step is omitted. Again, just to jog our memories, say you have a sphere which you want to print. If we go via the direct route, we'll simply section or slice the sphere itself, and in each contour of this slicing plane, you will end up with these exact circles. However, if we go down the indirect route, we'll first convert it into an approximate shape. So maybe something like a polygon, and then we section it or slice it. And in each of these slices, we'll end up with some polygonal shape, which will approach a circle, but will not really be a circle. So the object is positioned and oriented in the desired place on the build platform. And typically you want to avoid multiple horizontal surfaces, and you would tilt the build by 10 or 15 degrees. We'll also see why this is in detail, but primarily the reason is because we have discussed this in the case of WAC photopolymerization as well. The horizontal structures often require support material, especially in the case that they are overhangs. Now, these support materials will extend from this horizontal surface onto the build plate, or in some cases, from this horizontal surface onto the part that is being built. Later removal of these support structures often leaves remnants on the final build surface. And it might not always be possible to say get rid of these remnants. Thus, the surface quality of the part is affected. That is why typically we would want to avoid, say, or minimize the number of surfaces that are horizontal in any build. Next comes the slicing of the CAD model, and you set the machine with desired process parameters such as beam dia, beam offset, grid sizes for normal and fine grid cutting, number of dummy layers. So these are the layers that you start with. You paste a few number of layers of sheet onto the build plate before you start your actual building process, and so on. So your typical generic AM steps. Now the build process is where it gets interesting. So as we discussed, here is a schematic. So you have this material supply role on one side and this take-up role on the other. There also exist technologies which do not have a take-up role, but only one material supply role. The material, as we discussed, in the form of sheet, it can be a paper or a plastic sheet or even a ceramic sheet. You have this laminating roller which travels from one end to the other. So right here, and by its motion, it typically applies either some heat or some normal force on the sheet, or even a combination of both, depending on the type of adhesive we are using, and fuses this new sheet of material with the existing object that has already been built till here. Now, cubic technologies normally uses a laser for the subtractive step, and using a suitable combination of optics and an XY positioning device, or what we have come to know as a galvanometer. Is nothing but a pair of mirrors that are suitably aligned to each other and are attached to motors, which help in scanning this laser beam all over the region of interest. Now, in each pass, first you will have this parting cut where the exterior contour conforming to the whole larger build geometry is first scanned. Then you have the region of interest. So in this case, it is this donut shape. So this can be done using a fine beam diameter or a slower scan speed so that you can maintain precision. And then you cut out the grid lines, which can be done with, say, a beam of larger dia or at higher speeds. Because now precision is not so important. We would like to minimize the build time. So here is a typical sequence of the steps involved. Thin layers of adhesive coated material are sequentially bonded to each other and individually cut by a CO2 laser. As some of us might be aware, CO2 lasers are really, say, cost effective and they are also easily available. These days, they are available in most UG laboratories for DIY experiments and such. Also, CO2 laser beams are interact better with the type of raw materials that are used in a typical sheet lamination process, such as, say, ceramics or paper. In this case, the paper reel indexes by a fixed distance and has adhesive at the bottom surface being this one right here, the surface which will come in contact with the existing build. The table rises to the required height. This is because after each pass, the table lowers by considerable distance so that the cut portion is separated or removed from the reel. So now it will come back to its original height. The hot roller laminating tool rolls over the sheet, causing it to stick to the previous layer. Again, as I discussed, this might be by some normal pressure, some normal load, some temperature, or a combination of the two. The height is then ascertained and it is passed on to the slicing software in case there are any deviations which must be accounted for. Now the contours or loops of the slicer cut by the laser. It is possible to offset the laser beam in such a direction as to compensate for it. And here we may use a smaller dia or a smaller speed, a lower speed to ensure greater precision. This is followed by grid cutting around the bounding box of the stock. Now the grids of all the layers coincide, and why this is so is because at the end of the process, you will end up with a block, say a cubical block, and you will have all these grid lines. And when you remove them, if they are all aligned together, finally when you remove them, an entire cuboid-like structure will come out because they were aligned in each layer. This simply makes the removal of the excess material faster and easier. Finally, a parting of cut is made. So here parting of cut is the last step, but I have seen in the videos of the processes that often the parting cut is the first one to be made. And then to separate the build part, the table lowers by a significant distance, a pre-decided distance, and the process continues. So the typical major steps, a new layer comes, it is bonded by this hot roller, and then you have the cutting operations. So the parting cut, the contours, and these grids which must be cut out. However, in this case, rather than the building time, which was, say, the most time consuming process or the most time consuming step in processes like that, photopolymerization, or some of the other liquid AM processes that we looked at in the past weeks. In this case, the rate determining step or the slowest step is in fact the post processing step, which is typically called decubing because we are trying to remove these cubes or cuboids of excess material that are stored. So you see some of these parts which are removed. So once all the layers are made, the built volume is a rectangular block, and this is parted off from the table using a thin wire rope, um, typically in metal additive process. To separate the built material from the build plate or the substrate, we use wire EDM typically. In this case, it is just by using a thin wire rope. Now, the unwanted material inside and surrounding are removed using hand tools. Given that this is a manual process, it is slower than any machine-based processes. And also, now the skill of the operator or the skill of the technician comes into the picture. Thus, this process or the cubic technology's norm is not really a fully automatic process because the post-processing is manual. The skill of the technician will also play a role in the final finish of the part. This operation can take several hours. So the decubing process itself will consume several hours. The build process again will be in the order of hours, less than this decubing, and thus we can say that overall the process is very slow. The part and is finished and even painted if needed, and can be given some protective coating should the case be. This process or similar process have certain advantages. For one, in each layer, we saw that we are really interested only in the contours itself. Whereas in other processes, such as say VAT photopolymerization, we had to scan the boundary, but also we had to scan inside it to cure the entire surface or the region of interest. In this case, however, we are curing only the boundary or cutting only the boundary. Inside the material is present from before. Therefore, this build step is faster than other conventional AM processes because the speed is proportional to the surface area of the object and not to its volume. We are not really working on the insides of the boundary. Typically, LOM will employ a CO2 laser, which is cheaper and readily available. Again, it is only used for cutting, so control is also simple than for say curing or sintering type processes. No protective environment or say inert gas purging is needed or vacuum is needed. This can be performed in normal atmospheric conditions. We would, however, require a proper ventilation system to take away smoke or any other fumes which might arise from the process. Paper is a cheap feedstock, well, cheaper than metals at least. And the final part does have wood-like strength. And there's this beautiful analogy where we say that typically paper is made from wood. However, using this process, we are making wood out of paper. And the parts can be used for prototyping and for as patterns for casting. There are certain limitations to the process, however. One being the fixed layer thickness. So this is simply equal to the thickness of the sheet. And thus, if you have a build which is of a regular geometric shape, does not have regions with high curvature, this will still be okay. However, if you have a geometry which would have benefited from adaptive slicing, where you use thicker slices for linear or rectilinear regions and thinner slices for regions with high curvature, you lose out on such advantages and the final build quality and accuracy of your build is affected. Grid cutting and decubing take much more time than the object cutting or the actual building process itself. Decubing is time consuming, perhaps the most time consuming process. Horizontal surfaces pose problems because they might leave remnants of the material to be removed. The finish is badly affected. Because paper is a highly flammable material, this process is prone to fire hazard, and this technology itself is almost dead because of inadequate product development and marketing. So, example numerical on now, we'll also look at one. And this is a part which is built from laminated object manufacturing. The next technology or sheet-based AM technology is called Kira's paper lamination technology, which uses again paper as the raw material, uses a bond then form approach, same as the previous one. In this case, however, rather than a laser, we use a mechanical knife for cutting. The bonding is still an adhesive based, and joining occurs over the entire region of the sheet, including the undesirable regions. And it's given that most of the subsystems are the same, the working principle is mostly the same as laminated object manufacturing. Only difference being we are using a mechanical blade instead of a CO2 laser. What difference this introduces, apart from the say the very physics of the problem, is also the omnidirectionality. When you have a so this is a layer, this is your contour. If you are scanning it via a laser, it does not really matter whether I go this way, or do I scan half, then I start here again and scan the other half, or whichever way I go. Because the laser beam is omnidirectional, its property do not really depend on the direction of travel or traversal. However, typically you would use a blade which has only one cutting edge. Say this is a cutting blade that we are using attached to some holder. Say this is the cutting edge. Now we are constrained to always travel along this direction. Even if we have two cutting edges, we can only move along the plane. We cannot say we want to move out of this paper or into this paper. That is not possible because that is a flat face that cannot cut the contour. Thus, the omnidirectionality of the process gets affected, and we must take say extra care in the process planning step to ensure or to come up with suitable tool paths. The process is very much like a laser printer, and here a toner is used as the binding agent. Lamination again is done by a hot plate. Remember in the previous case of laminated object manufacturing, you had a roller which would roll across the surface from one side to the other. This offers certain advantages. One is that the pressing action itself is more uniform because now you're pressing over an entire area compared to in the previous case a line by line pressing, and layers do not slip due to the shearing. This process therefore was also formerly known as selective adhesive and hot press. The typical build volumes of this process are smaller than cubic storm, but on the other hand, they tend to be more accurate and have better geometrical control. And only one roller is used in this case, which is the material supply roll. There is no take-up roll in this case. The pre-processing is much the same. There is also the pasting of a few buffer layers, and given that here the sheet, the raw material is in the form of paper sheet, typically you will use just some adhesive glue. Adhesive glue such as your basic stationery glue, like Fevigum, is also used in the case of, say, fused deposition modeling or the 3D printing of polymer filament-based polymers, where you use glue on the build plate for the very first layer, and this further enhances the adhesion of the first layer to the build plate. This addition of the first layer is very important in all other additive processes as well. Like I can give you an example. Typically, in the case of DED, the case of DED as well, for the first layer, we only use say 90% of the printing speed. If you have set the machine to some print speed, say 1000 millimeter per second, For the very first layer where the material is deposited on the substrate itself, it will typically print at 900 millimeter per second. And this is to ensure that that first layer adheres well, because often it is the source of most problems. Later layers where you have to deposit the material on the pre-built material of the same type are easier to be performed. Now the build process here, first you have a sheet alignment mechanism. Because you do not really have a take-up rule, you only have one material supply node. You do not really have tension to control the motion of the sheet. Thus, you must have an alignment mechanism which adjusts the printed sheet of paper onto the previous layer. A hot press or something like a hot iron then moves over them with the printed sheet pressed to the hot plate at high pressures. So here you have a combination of heat and pressure. The temperature controlled hot press will melt the toner which is on the bottom surface of the sheet, and this toner then helps to bind this sheet with the previously deposited layers. The hot press will also flatten the top surface and make it flat and smooth, and will prevent the formation of any voids or air bubbles between sheets. Now your computer will measure the amount of movement up to the hot plate and will compensate for any deviations should they occur. A mechanical cutter will then cut the top layer of the block along the contour of the section, as well as a parting cut to separate it from the excess paper. These steps are repeated until the entire model is built. Again, the depth of cut must be carefully controlled to ensure that we are not really damaging the already deposited layers. Uh, in the videos, we also saw during this week's lectures, we also saw a video of the Kira's paper lamination technology and observed how, in a very compact setup, it prints parts with reasonable geometric accuracy. Here is also a schematic representation of the same. So here you have the material supply room or the paper room. This passes the sheet of material onto the build area. You have this heating plate which comes in contact with the paper and activates the resin which bonds this to the previously deposited layers. And here you have the cutting knife which cuts the exterior contour, the grid lines, as well as the parting bit. And here is an example video which shows how the decubic operation is performed. So again, the operator will use some mechanical implements or hand tools to remove all of these cuboidal structures which are all the undesirable material left over. Kira's paper lamination technology offers certain advantages. It uses a flat plate and high pressure along with heat to bond the layers together. Each layer is pressed with a flat hot plate and the model remains flat during the entire build process. There is no shearing, such as in the case of laminated object manufacturing, where you have a hot roller rolling across the surface. In such cases, you might also observe slippage, and this slippage will lead to either the trapping of, say, air bubbles between the sheets, or it will wrinkle the surface of the sheet, or in some cases, it might also lead to geometric inaccuracies because now you have because of slippage, you have either the amount of sheet which is contained in that particular layer may be less than or more than the desired uh, area of sheet. All of these things are taken care of using the flat plate in this case. Now, since the block is released after cooling, the internal stresses or the residual stresses are also allowed to get released. Thus, there is minimal residual strain or internal strain, and there is little to no curling in the final model. It uses a computerized mechanical knife to cut sheets of paper, which results in a smooth surface for the build model. Since we are not using lasers, there is no fire hazard, and the release of fumes or other gases is also almost non-existent. The high lamination pressure used in the paper lamination technology has resulted in products that are 25% harder than the equivalent wood. So previously we were just comparing this to the analogy of having made wood from paper, but now your wood is also 25% harder than natural wood. This is often strong enough for most prototyping applications, including sandblasting. Here are some disadvantages. Again, the layer thickness is fixed, and this will be true for most, if not all, sheet-based AM processes. You cannot really exploit adaptive layer slicing. Grid cutting itself takes more time than the object cutting. Thus, your post process or your wasteful cut takes up more of the productive time than the building process. Decubing is the slowest and the most time consuming process. Horizontal surfaces again are a problem. Next, we have this plastic sheet as a raw material, and the technology is called solid dimensions plastic sheet lamination. The subsystems are illustrated here. So the raw material is plastic. The approach remains bond and then form. Cutting method again uses a knife. You have an adhesive. However, in this case, rather than joining the entire sheet to the previous one, we are only joining some selective regions. Say if this is the contour in my n plus 1h sheet, and this is the corresponding contour in the NH sheet. Now only these contours will be joined. The rest of the material, the rest of this sheet will not be joined, and we'll see how this is accomplished. So solid dimension uses thermoplastic, which is a transport material, as a raw material. Here we use a combination of the adhesive and a release agent or a masking agent. For binding the sheets, and a support removal method called peel away is used, which is easier than decubing. So in any layer, say this is my contour, then first what happens is all of this remaining region will be covered with the masking agent. And then you apply the glue to this region of interest. Now you have the next layer, and a similar process occurs. So all the undesirable region is covered with a masking agent, and the desirable regions are covered with glue. Now, when you bring these two layers, say the NX and the N plus 1F layer in contact, the regions covered with the masking agent will not bond together. It's only the regions that are covered with the glue which will bond together. And a beautiful analogy which was shared by Professor Kapil was that of water and adhesive tape. So if you're covering a surface or you're sticking two, say, sheets of adhesive tape, if you put water on some regions, the regions which have water will not really stick to each other, whereas the remaining regions where you have only the glue will stick. So here the water is the masking agent, whereas the glue in the adhesive tape is the adhesive agent. Once these regions are stuck together, you will cut away along these contour lines using the mechanical line. So till now, while we had stuck the glue, this piece was still whole in, in the sense that the sheet was still There was no parting cut made. Both the desirable and the undesirable regions were part of the same sheet. So now we'll perform the cutting operation, then we'll trim, and then the process continues. Again, there is something called a peel away, where you stick the support structure in each case. Say if you have support here, then you'll stick to this, maybe in the previous layer, somewhere here, and so on. Such that there is this continuous network of support materials from one layer to the next. And finally, what ends up happening is from the topmost layer, we pull along this, and from each layer, the support structure will unravel and can be taken out very easily. This has also been illustrated in the video, which was shown in the lectures. The next technology is CAMLEM's CL. I believe this CL name is simply coming from CAMLEM, which uses ceramic sheets as a raw material and uses a form and then bond approach. So this is different from all the processes we looked at till now. For cutting, it will use a laser because to cut a ceramic sheet, a mechanical knife may not always be the most appropriate method. To join the ceramic sheets, we'll use sintering, and again the entire region, including the desirable and the undesirable region, will be joined together. In essence, CAMLEM stands for Computer Aided Manufacturing of Laminated Engineering Materials, and you just shorten them to form CL. It is based on the principle of form and then bond. It is possible to process a variety of materials in this machine, ranging from ceramics to metals. And a single machine is capable of processing up to 5 materials. So this is a very useful multi-material process. Here, the functioning of such a typical machine is also illustrated. So just like before, we in the post pre-processing steps, you have a solid CAD model, and then you have its contour representation after its interaction with the slicing planes. Then we cut the slice in each such plane using a laser, and at this stage, each slice constitutes a green object. We know that in the parlance of centering methods, green object is the object or green part is the one which we have before centering. So say it might be pressed together in a cold press, or in this such as in this case, it might be just a cutout from a slice, and it is called green because it is not yet centered and it has very poor strength. So there's a high chance that if we apply some mechanical forces, the part will deform at this stage. Thus, we must take care while taking it from one process to the next because it has very poor properties. The next step is stacking. So here we see that in each layer, you have these two holes which actually act as the reference along which these parts from each successive layer can be stacked. Say you have these two rods or two bolts and they act as a reference. So each hole is aligned with these bolts or rods, and then they are just placed on top so that you have perfect alignment or precise stacking. Then this entire, after putting all the layers together, you put this entire, say, assembly of layers into something like a hot isostatic pressing machine so that the particles can get centered as well as the voids can be minimized using the HIP process. Here you see that during the centering, the conventional binder removal process will also occur, whereas in the case you have some binding agents to the ceramics, they will get released because of the high temperatures, and the ceramic particles will center with each other. So you will have the typical, say, necking process, and then finally you will have a bond between these two particles, and you will have a finished component. Of course, in such cases, you will have to account for shrinkage of the part. The hot isostatic pressing step will take care of the porosity. Here, the model that was described is called CL100, which has a build volume of 150 cross 150 cross 150 mm and layer sizes varying between 100 and 600 microns. It has certain advantages. One, of course, is the ability to process multiple materials, ranging from ceramics to metals. It is possible to form internal channels because it's a layer by layer process. You just uh, machine or cut out the region for the channel in each layer and then stack them and then center the whole thing. No precise depth of cut required as it is form and bond approach. So again here you might have something like a sacrificial plate at the bottom. Because you might not be very precise even if you happen to cut some part of this plate. It is still okay because it is sacrificial to begin with. It's not like there is some pre-deposited layer at the bottom which you run the risk of damaging. No unwanted glue material. Here there is no formal adhesive step. We just put the entire assembly in the hot isostatic process, in the hot isostatic press, and through the action of sintering, the ceramic particles will bond with each other. Because of the sintering, the particles will also have great strength, which will be greater than achieved by any adhesion process. And variable material and layer thickness is possible depending on the height of your feedstock or the thickness of your feedstock sheet. Certain disadvantages, however, are also associated with this process. One of them, as we talked about, is shrinkage. Typically, after any sintering or HIP process, you will have to account for shrinkage. So typically, you will start with a volume which is say 5% greater than your final intended volume. This is the shrinkage allowance associated with the process. The alignment must be very precise. Like in this case, you had these two reference holes in each layer, which could be used for alignment purposes, but your geometry might be such that it does not really have the provision for such reference holes. Or there might only be a few layers where still such reference holes are available, and say after this point, maybe the next layers were fully solid. So aligning them will become a very uphill task. Also, you have to maintain this alignment while taking the assembly from one process to the next. Say once you have aligned them, while you're transporting them to the hot isostatic press, you have to ensure that the alignment is maintained. If by any mistake or by any motion, if the alignment is disturbed, then the final part will also not conform to the design geometry. And it is not really possible to have explicit supports. However, given that we typically use ceramic or metallic sheets, this disadvantage might be subverted to some extent. However, in certain cases where you need explicit supports, there is no provision of having them. The next one is NX Corporation's offset fibers, which again uses plastic as the paper as the raw material, uses a form and then bond approach, has a mechanical knife for cutting, will use an adhesive, and again the entire region is joined. However, this is somewhat different from the classical processes that we have looked at till now, and maybe that is why it does not really have a lot of, say, commercial implications either. However, for the sake of completeness, we'll just look into it. So it is somewhat similar to Kira's paper lamination technology. The main difference between the two being that this offset fibers uses the form and then bond fabrication method. So you have this carrier plate over here, and on top of it, you put your layer of material. Then you use a mechanical knife to cut the outline of the layer. Once the outline is cut, along with any cut lines, such as shown here, the entire layer is then transferred and laminated onto the previous layer using this carrier plate. This is the carrier weeded material or the material which will not be part of the next deposition layer. It will simply be removed. And the process of cutting and laminating of the material is repeated until the whole model is built layer by layer. And as we can tell, again, proper alignment and precise alignment will play the major role in deciding the final part accuracy. Thin fabrication material, such as thin film that can be cut and bonded to itself by means of adhesive, are rested on this carrier plate. A 2D plotting knife is used to cut the outlines of cross sections into the fabrication material without cutting through the carrier plate itself. So again, precise control of the depth of cut. The plotter will also cut the parting lines and outlines. The film is then weeded to remove some or all of the negative material on the undesired regions. The film is then inverted with the carrier plate, so the carrier is facing up, and the cut pattern is brought into contact with the top of the glowing object and bonded to it using some adhesive. The carrier is then peeled off to reveal the new layer, and a fresh surface is ready to bond to the next layer. It can work with a wide variety of materials and has minimal shrinkage since there is no, say, heating or sintering step involved. The other advantages and disadvantages are similar to LOM. However, you need precise cutting forces so that the carrier plate itself is not damaged. The alignment between the new layer and the previous layers must be very precise, and you'll end up wasting a lot of material. However, this is common to almost all the sheet-based additive manufacturing processes. The final two sheet-based AM processes are ultrasonic consolidation and laminated manufacturing. So ultrasonic consolidation uses a metal sheet as the material and uses a bond and then form approach. It uses milling operation as the cutting method, and bonding occurs via diffusion, solid state diffusion, and only the selective region is joined. Again, using the hybrid additive manufacturing method based on ultrasonic metal welding of a sequence of metal files with in situ material removal process. So 3-axis CNC contour milling. Now, because of the applied pressures, which are moderate, and the relatively lower temperatures, which will be say 30 to 50% of the melting point, UC operates as a solid state process. Works on the principle of bond and then form, and it was invented and patented by Sourav in 1999. Later, Sourav collaborated with the Edison Welding Institute to start a company called Cabrisonic. We'll go into the depth of the working principles of such a technology. So, your machine is connected to this typical power supply of 50 hertz, and this frequency is amplified or converted, transformed to a much higher frequency of 20 kilohertz. Then this electrical energy is converted by a transducer into mechanical energy. The amplitudes are boosted using a booster, and then this vibration is transferred to the sonotrode along with the application of normal force to diffuse or to bond the material with the previously deposited structure. So your power supply converts the mains electricity AC current to an ultrasonic frequency that is 20 kilohertz typically. This in turn is converted into mechanical energy using an actuating transducer, and the transducer then mechanically drives a booster and a sonotrode. The sonotrode applies the ultrasonic oscillations to the metal foil material with the action of a compressive normal force. Here is a 3D representation of the same. So your welding speed is basically the speed with which your roller or sonotrode is moving along this foil. You have the transducer, booster, and the sonotrode. The welding force is a normal force acting on the sonotrode, and the oscillations are occurring in the transverse plane. You have an anvil, the previously bonded points, and the new foil layers being bonded. In this case, the typical layer thickness is approximately 100 to 150 microns only, and typically 25 mm wide. Why 25 mm? It is actually 25.4, which is nothing but 1 inch. And you will also see this is the case with other processes such as in FDM. The filament material has some typical value, and that is only because the first technology which was commercialized uses that diameter of filament. There is no other scientific or technological reasoning behind it. Similarly, for say wire-based AD processes, we typically use wires of the diameter of 0.8, 1 or 1.2 mm. Again, that is because welding wires are mostly available in those diameters. Similarly, here the sheets are similarly 1 inch wide. There is no other scientific or technological reasoning to this. It's just based on the available standards and the available materials. The thickness, however, is 100 to 150 micron, which is very good and which allows very precise control of the geometry of the deposited material. This is placed on a sacrificial base plate that is bolted to an anvil because it should be able to take the ultrasonic forces. The foil is compressed under moderate pressure by a sonotrode that vibrates nominally at 20 kHz, and the amplitudes range typically in the order of 5 to 40 micrometers in the transverse direction, so perpendicular to the direction of travel of the sonotrode. The sonotrode will travel along this sheet, whereas the vibrations, as we can see, are occurring perpendicular to it. The sonotrode has a roughened surface to grip the top surface of the foil. This is typically achieved via a knurling operation, which introduces some texture on the surface of the sonotrode. Why we want this is so that there is no relative motion between the sonotrode and the foil. We want them to move as one. For this, we need high friction between the two surfaces, and to enhance this friction, we typically have this knurled pattern on the surface of the sonotrode. Now that the sonotrode and the foil will move as one, there will be no relative motion. The only relative motion now happens between the sheet or the foil that is being deposited and the previously deposited layer or the base plate. Now, performing this process at room temperatures produces heat through the scrubbing of the meeting surfaces or frictional heat at the bonding interface. This heat causes a temperature rise at the interface that is between 30 to 50% of the base metal's melting temperature. Typically, the ultrasonic consolidation process is conducted at 200 degrees Celsius by employing a heated base plate. This just makes the material more amenable to plastic flow, and thus we can work with lower normal forces. Once the layer is bonded, additional layers are added and the undesirable regions are machined using this CNC milling step. The process is repeated until the desired dimension of the feature are reached. So here we are seeing the buildup of this complex structure. In each layer, the sheet is added. The sonotrode moves along it to bond the sheet to the previously deposited material. Then you have this CNC milling cutter, which is removing all the undesirable regions, and then the next layer is also added. We'll delve somewhat deeper into the working principles of this process. And in terms of comparison to, say, existing or standardized processes, UC may be said to lie somewhere between the solid state diffusion bonding and the linear friction welding. And let us see what are the similarities and dissimilarities of this process with these existing ones. So in solid state diffusion bonding, you will have no scrubbing of the two surfaces because there is no relative motion. It's just that they are held together under some normal load. The diffusion bonding relies on elevated temperatures, so you have a lot of heating, 50 to 90% of the melting point of the material, and high pressures as well. Flatten the bonding surfaces. Again, the surfaces must also be cleaned thoroughly for such a diffusion couple to be made. To flatten the bonding surfaces, fragment any impurities that might remain, and produce atom to atom contact, because here you are relying on diffusion for bonding to occur. You have this boundary between the two surfaces, and you want to join them via diffusion. So you must affect the transport of atoms, say, from one interface to the other. However, atomic diffusion occurs at very small length scales, so they must be brought in close contact. Secondly, if the surface is dirty, the diffusion process might be hindered, so you have to clean the surfaces. Again, you need high temperatures to energize the atoms for such diffusion to take place. In the ground state, they will not want to diffuse across the interface because there is no driving energy. When the surfaces are pressed together at high temperatures, atoms diffuse along the grain boundaries, closing voids in the contacting surfaces and producing a bonded structure. The atoms condense and further reduce the size of any voids in the interface. The pressure can be applied starting from a few minutes to up to a few hours, or in certain experiments, even for few days or weeks, depending on the material being bonded, the extent of material diffusion that we are looking for, the strength of the material that we envision, and so on. On the other hand, in the process of friction welding, the bonding is solely dependent on the pressure and frictional scrubbing at the interface. So here you do have relative motion. The process begins with two pieces that are statically clamped. So no motion, first only normal loads. Then, depending on the process, you can have rotation in the case of inertia welding, or you can have this linear reciprocating motion as shown here in the case of linear welding. The pieces are then brought together under light pressure. Remember, in the previous case of atomic diffusion, it was high pressures, which causes frictional heating because of the relative motion between the parts. Finally, a forging pressure is applied and the relative movement is stopped to form the final joint. The stresses on the material to scrubbing and forging cause the material to reach its plastic state. The heating of the build plate up to 200 degrees Celsius, as we read, also helps to accentuate this process, and this removes the surface impurities. After the plastic state has been reached, the two surfaces are forced together to form a mechanical joint. Now, ultrasonic consolidation shares several aspects of both these processes. It is performed at elevated temperatures up to 200 degrees, similar to diffusion bonding, and the interfacing motion of the friction welding. It is unique in the sense that ultrasonic waves travel through the bonding material and lower the elastic modulus and the stress value needed to reach a plastic state by something called acoustic softening, also called the Blaha effect. I'm sure it is mentioned in the slide somewhere. That when you have ultrasonic waves traveling through a material, we find that the elastic modulus of the material is lowered, as well as the stresses that must be overcome to reach the plastic state become lowered as well. In fact, experiments show that the use of ultrasound in diffusion welding in an inert gas atmosphere or a vacuum even reduces the time needed for bonding. The mechanism of bond formation during UC has been widely studied. However, the exact workings are still under research. So when Uh, One of the theories is described here. So when two relatively flat surfaces are brought together, only the peaks of the surface asperities actually touch. We know that whenever we are talking about a smooth surface, no surface is atomistically smooth. You will never have just a plain surface, however much you magnify it. There will always be some asperities in terms of these hills and valleys. When we are bringing any two such surfaces in contact, only these asperities will be in contact. The valleys are not in contact. Thus, your actual area of contact is much lower than the geometric area of contact. The physical contact area is less than the geometric area of contact, and ultrasonic consolidation causes the physical area of contact or the actual area of contact to approach this geometric area under the combined action of the normal forces and the ultrasonic waves. Ultrasonic motion causes the surface oxides to break up, also as an effect of acoustic softening, which allows the direct contact of pure metal, resulting in metallic bonding. These bonds are in turn plastically deformed by shear vibrations, resulting in heat, which promotes diffusion and crystallization of material between layers, resulting in a true metallurgical bond. In addition, the process is also aided by the transfer of ultrasonic energy into the metal, which effectively acts similar to localized heating, reducing the stress needed to go into the plastic zone. And this has been described in the Blaha effect. So, when ultrasonic energy interacts with a material, it shifts the stress response curve by reducing the amount of heat and stress needed to reach the plastic stress state. This is called acoustic softening. The process parameters which are important for this process and their effects are also described. So first is the travel speed or the welding speed. It is the speed at which the sonotone is traveling along the sheet, and this determines the energy exposed per unit length of the welded track or the linear or area energy density. The amplitude of vibration of the ultrasonic waves, which is typically of the order of say 5 to 20, 5 to 40 microns. Higher the vibration amplitude, greater the ultrasonic energy delivered. A sufficient amount of ultrasonic energy is required to plastically deform the material and fill the voids between the sheets. However, if the amount of input energy exceeds a critical level, the excess plastic deformation may damage the previously formed bonds at the interface, which is undesirable. Next process parameter is the normal load. This compressive load actually flattens the asperities and determines the magnitude of the limiting value of friction force, consequently also the stresses at the interface. A sufficient amount of normal force ensures sound metallurgical bonding across the interface. If the normal load exceeds a critical level, the excess plastic deformation may damage previously formed bonds at the interface, similar to excess amplitude. The base plate temperature would serve to reduce the apparent stress for plasticity, enhance the atomic diffusion, reduce the strain hardening due to plasticity, and have other beneficial effects. The texture on the sonotone is a necessary evil. We know that some texturing is required to enhance the friction between the sonotone surface and the foil surface. However, if the texture is very deep or is somehow unsuitable in any other aspect, then that might lead to the formation of voids on the surface or might even affect the surface finish if it is done on the top sheet. The sonotone texture directly affects the amount of damage to the surface of the bonding strip. Excessive damage may lead to large gaps. Also, it affects the gripping edges of the sonotone strip's top surface. Ideally, the texture should grip the strip strongly enough so that there is no relative motion. However, the texture should not be detrimental to the build quality itself. The electrical power draw is a measurable quantity that may reflect the different conditions of stick and slip at the interface. The sonotone typically requires more power to counteract friction when it is sliding rather than when it is sticking. The stiffness of the machine directly affects the amount of force transmitted to the bonding interface. These were the process parameters. There are also some material parameters which affect the process. One is the surface topography or the surface quality of the sheet, which affects the initial contact area through the touching of asperities and therefore influences the frictional and normal stresses of the interface. Then there's the presence of surface contaminants and oxides on the foil surface, which may prevent metal to metal contact, and they must be destroyed or somehow displaced in order for bonding to begin. Then the stiffness of the material, which directly influences the resistive force produced by friction at the bonding interface. Next is hardness, which again influences the coefficient of friction and empirically has also been shown to influence the amount of energy required for bonding to occur. One of the unique applications of this ultrasonic consolidation process is in the integration of sensors, actuators, and reinforcement fibers within the single metal matrix. So here we see that between two sheets, this one and this one, you have these maybe optical fibers which can be easily integrated without damage. And when you pass light from one end, it is visible on the other, which shows that the damage, the fibers are remain undamaged. This can also help in the manufacturing of metal matrix composites, which can have suitable, tailored, or desirable properties, which will be a combination of the matrix and the reinforcement phases. Some researchers have also incorporated channels for fibers using laser beam melting. Another advantage of the ultrasonic consolidation process is that it allows us to form parts with multi-material combinations, which would typically not be possible through the melting route, because upon melting and mixing, these might lead to the formation of certain undesirable or deleterious secondary intermetallic phases. Given that the ultrasonic consolidation process is a solid state process and does not go through the melt route, it even materials which are typically do not mix together, such as iron and copper, or which may form intermetallics, can be bonded together. The modeling of this process has also been described here, so we'll let us just go over it briefly. Here you see the free body diagram of the interface between the newly deposited sheet and the previously deposited material of the base plate. You have the normal load P acting, you have the friction force Fs between the sonotron and the new material or new sheet of material being added. Then you have the friction force Fa between the previously deposited sheet and the anvil. If you separate these two, then on the new sheet you have Fs, Fi, and P, and on the previously deposited material, Fi, Fa, and P again. The equations of motion of these material can thus be written like this. So for the sonotron itself, we know that it will follow some sine or cosine type function. This d naught is the maximum amplitude of this vibratory or oscillatory motion. Once we have the displacement, we can just differentiate it to find the velocity and the acceleration of this motion. And thus, on the top surface, the equilibrium of forces will give us Fs plus Fi equals mass times acceleration. This mass is of the strip in contact with sonotron, which can again be modeled from the contact length between strip and base, the width of the strip, and the thickness of the strip. Why contact length? Because ideally the contact between the roller and the strip should only be at one point. However, we know that this is never really true, and under the action of Hertzian contact stresses, there will be a finite area or a finite length of the sonotron which is in contact with the sheet. It is never truly at just along one single line or in 2D plane along just one point. Fs is the friction force between the sonotode and the strip, and this is simply equal to mu times p, p being the normal force, and mu is the coefficient of static friction. Why static friction and why not dynamic? That is because, as we already discussed, there should be no relative motion between the sonotode and the sheet being deposited. They should move perfectly with each other. Thus, the friction in such case would be static friction only. The contact length between the two materials can be calculated from contact mechanics, and the formula is shown here. And thus, the force Fi can be calculated here to account for the direction of this frictional force, which will always be opposite to the direction of motion of the sonotone. We have this sine term, which is simply given that we know that the direction of the friction force will be opposite to the direction of motion of the sonotone. You first find the direction of motion of the sonotone as Vt by norm of Vt, and then you add a negative sign to account for the opposite direction. Thus, we have the Fi term. Once this interfacial shear force term is known, we can find the energy input in each cycle. So we know that power is equal to force into velocity. This is one of the formulae which we used in our 11th and 12th physics classes. If we just integrate this differential power over the time of action, say some 0 to t, we'll end up with energy, and this is exactly what is done here. Even the dwell time on each point can be calculated, and then we have the number of motion cycles when the sonotode is above the contact area, and the total energy supplied thus will be equal to the energy supplied in each cycle multiplied by the number of cycles. Now, as we were discussing, ultrasonic consolidation offers several advantages compared to other processes. It allows the embedding of temperature and pressure sensitive objects into the solid metal matrices, such as fibers, shape memory alloy fibers, optical fibers, electronic sensors, and so on. This is permitted because of the low temperature and high plastic flow of the metal matrix. No atmospheric control, such as purging with inert gases or maintaining a high vacuum, is needed because it is simply a solid state room temperature process. It has no known safety hazards associated with the formation of liquid metal, metal fumes, powder handling, dust, or any other molten metal handling issues. Again, due to the absence of any liquid to solid transformations, the residual part stresses are minimized, and even the shape distortion in comparison to other processes is very low. Now, UC deposition rates are far higher than many layer manufacturing processes due to larger deposition spot size, which is 1 inch as we discussed, and lack of any lending post-processing procedures, because whatever post-processing removal has to be done happens in the same step using a milling cutter. UC can be used to bond materials which are metallurgically incompatible, or which, when say mixed together in the liquid state, may lead to the formation of undesirable intermetallics, such as aluminum, titanium, copper, nickel, which have very good solubility, stainless steel, and so on. UC is a highly energy efficient process, consumes only as much as 5% of the energy required for even conventional welding. Then we have this last process, which illustrates the making of tool and punch and die arrangement. So this is how you can use it for tooling purposes. In this case, we preserve both the desired contour as well as the remaining undesired part, and we keep stacking them separately. So here you have all the undesirable regions stacked into one with careful alignment, and here you have the desirable regions stacked into one. Once this is done sufficiently, you end up with a punch and die to make this objects of this shape in the future using some forging type of arrangement. And this is also illustrated here. So now we have gone over all the concepts that were covered in this class. In this previous week, we'll look at a few example problems after a short break. So, welcome back, and let us look at a few illustrative problems that will help us revise our concepts and help us solve the assignment questions for this week. The first question asks us, which of the following materials cannot be processed by sheet additive manufacturing processes? And among the options are listed two grades of aluminum, say aluminum 6000 series, aluminum 7000 series, and copper. Or is it that all of the above can be processed via ultrasonic consolidation or similar sheet additive manufacturing processes? So, in the course of our discussion, we found that the type of material, or not just one single material, but even the metallurgical compatibility or the lack thereof in the case of multi-materials, is not really a factor when working with sheet-based AM processes, because often they might just be in the solid state itself, such as ultrasonic consolidation, whereby we can process all of these materials even if they were metallurgically incompatible and may form some deleterious secondary phases when mixed together in the molten state. Thus, all of the above materials can be processed. The second question, the amount of ultrasonic energy delivered is directly proportional to amplitude of ultrasonic vibration. And we also saw this in the formulation or modeling of the ultrasonic consolidation process. Can we then use an arbitrarily high value of amplitude for ultrasonic consolidation? And let us look at the options. Yes, we can use, because the speed of travel scales linearly with the vibration amplitude. No, because the process approaches linear friction welding. No, because it can lead to cracking. No, because a very high energy input can lead to melting of the feedstock. So if we go in reverse, we know that a high energy input can indeed lead to melting. We typically want the temperatures to be remain within, say, 30 to 50% of the melting temperature. If by giving a very high energy input per unit area, we may approach the melting region, in which case metallurgical compatibility, residual stresses, phase transformations, and several other effects will come into the picture. So we should not really stick with or go up to an arbitrarily high amount of amplitude. It can lead to cracking, as we saw from the slides, that the bonds at the solid surface or the diffusion surface can be ruptured by the are indeed ruptured by the ultrasonic vibrations. And if the value of the amplitude becomes very high, that is above the 5 to 40 micron typical values that are usually exercised, it may happen that the bonds are ruptured irreparably. They cannot, the atoms cannot bond together again. And you end up with these permanent cracks at the interface, which are highly undesirable. So we should definitely take into account the possibility of cracking. No, because the process approaches linear friction welding. This is not really a challenge because, as we saw, the UC process does indeed take over or inherit certain aspects from the linear friction welding. So this is not really a concern. And because the speed of travel scales linearly with the vibration amplitude, this might not really be true. And it is wholly possible that the vibratory motion along the transverse direction and the travel motion along the foil may be independent of each other. So options C and D are correct. Which of the following regions are subjected to relative motion in an ultrasonic consolidation process? Is it the sonotrode sheet interface in the welding direction, the sheet interface between new layer and previously bonded layer, the interface between two previously bonded sheets, the sonotrode sheet interface in the transverse direction or the amplitude direction? Let's just draw a quick schematic and this will help us. So maybe this is the anvil. These are the pre-deposited sheets of material. This is the sheet of material which I am currently depositing. And here is my sonotrode. That's a very bad drawing. Now let's look at the interfaces that have been spoken of. The sonotrode sheet interface in the welding direction. The welding direction would be along this. And here we see that because of the motion of the interface, the sonotrode in this direction, indeed there is motion because this sonotrode will roll along the surface. So there will be some relative motion between the sonotrode and the sheet in the welding direction. Sheet interface between new layer and previously bonded layer. So this region. And we know that in ultrasonic consolidation, it is the relative motion between the new foil and the previously bonded foil, which leads to the increase or rise in temperatures and the solid state fusion. So option B is also correct. Interface between two previously bonded sheets, say some interface here. However, we know that once the material is bonded, there the relative motion between these bonded layers cannot be permissible because this will lead to deformation and cracking of the built part. So option C is not correct. Sonotrode sheet interface in the transverse direction or in the amplitude direction. So if we see the front view, this is my sonotrode and this is the sheet which is being deposited. So it has a bit greater than the sonotrode. This is unrealistic still, and this is the direction of the oscillatory motion. So we read how here we do not want any relative motion, and this is why we go to the trouble of knurling the surface of the sonotrode so that there is very high friction between the sonotrode surface and the new sheet of foil, and there is no relative motion. So while in the welding direction, as shown here, there is relative motion between the new sheet or the new foil and the sonotrode. Along the transverse direction or the amplitude direction of vibration, there is no relative motion. Whereas to find the directions of relative motion, so even this is wrong. So options A and B are the correct options. Question 4 is asking us, what is the Blaha effect, or as we read about it, acoustic softening? The flow stress decreases when an oscillatory stress is superimposed to a deforming specimen. The flow stress increases when an oscillatory stress is superimposed to a deforming specimen. The flow stress decreases when a constant stress is superimposed to a deforming specimen, and the flow stress remains unchanged when an oscillatory stress is superimposed to a deforming specimen. So there are two aspects here. One is the type of stress, whether it is, say, constant or oscillatory, and the other is the effect on flow stress. Does it increase? Does it decrease? Does it remain equal or unaffected? We have to examine both these aspects. Now, in the case of ultrasonic consolidation, we saw that the type of acoustic vibration that we are imposing is oscillatory, it's a vibratory motion. Thus, the stresses which will uh, superimpose or which will subject the sheet to is also of the oscillatory kind. The shear stress is oscillatory. It does not have a fixed direction. And we saw how, with the application of this ultrasonic vibration, the flow stress or the stress needed to enter the plastic deformation zone came down. That is what made the bonding of the sheets easier. So the flow stress decreased when an oscillatory type of stress was superimposed to the deforming specimen, and option A is correct. Question 5 is asking us which step determines the productivity rate in cubic technologies, LOB or laminated object manufacturing? Is it grid cutting? Is it the outer contour cutting? Is it the sheet or paper indexing time? And is it the decubing operation? So if we are to compare these times, so say this is option A, so TA, TB, TC, and TB. What we can say is that the paper indexing time perhaps is the smallest. Also, it is constant for a build. Then the outer contour cutting time, which may be lower than the sheet indexing time if the only very small contours are needed in one layer. However, typically for the general case, we can assume that it is just slightly larger. Now you have the grid cutting time and the decubing operation, and we saw how the decubing operation takes hours, while the grid cutting will take a few minutes at most, if not seconds. And to determine the productivity in cubic technologies now, we will have to look at the slowest step or the rate determining step. So in this case, option D, the decubing operation determines the productivity rate. Now, question 6 is a numerical example similar to one that was covered in the lectures. We have to find the ratio of time taken for grid cutting to the time taken for scanning the outer contour for the given geometry. And this will give us some idea of the time scales which are needed for the actual contour cutting operation, which is the main build operation, and the grid cutting, which is in fact an operation which removes the undesirable material. And as we remember, so there were many cuts, and in a particular sequence, they may be number one, the parting cut, which had to be made, which is this one, this contour, which is in fact the contour of the cuboidal or cubical build. Next was the cutting of the contour itself, and there might be exterior contours and interior contours. And then you have these grid lines, which are utilized for the later decuring operation. You have to find the ratio for the scanning the outer contour and the grid cutting. So let's start with grid cutting, and it will be noted by TG. We know that this in any long process, the build time is proportional to the surface area and not really the volume. So TG for each layer will be proportional to simply the perimeter which has to be scanned or the length which has to be scanned. So just like in the lectures, this will be, or maybe we can even describe how we come to this. So this will be proportional to, say if we are going row wise, so 1, 2, and 4. So 4 times A, and then you have the twice elements. So 1, 2, 3. I counted wrong because we might be using different lasers for die or different speed for cutting this exterior contour. It's best not to count that. And since we do not have a separate term for the part to cut, we can maybe take that in part of this detailing. When it comes to the the smaller grid line, 1, 2, 3, 4, and 5, we have 6, 7, 8, 9, and 10. So we have 10 times 2A. And because this build is is symmetric, that is whether you work along rows or along columns, you will end up with the same results. You will simply multiply it by 2 for both cases. And you are also given the relation that 1, 2, 3, 4, 5, 6, 7, 8, 8 times small a, which is the dimension of each of these smaller squares, is equal to capital A. Therefore, Tg can be equal to some constant times 2 into 4a plus 20a equal to 2k times um, in terms of small a 4 into 8a plus 20. So this is 2k times 32a plus 20a, which is 52 into 2, 104k. Now, similarly, if you want to find out the time taken for scanning the contour, it will be denoted by say, some other notations. So that they are scanning into B, T, C, then for a constant scanning speed, which will typically be the case, PC will be proportional to the length of this contour, so which is 4 into D. And if we assume the same proportionality constant, this will be simply K times 4D. Now D in itself is equal to 4A, as we have 16 times AK. We have to find the ratio of grid cutting time to time taken for contour scanning. So grid cutting by contour 104 Ka. Here we have 16 Ka. The constant, the K and A terms are cancelled. 104 by 16, 52 by 8, um, 26 by 4, or 13 by 2, which is equal to 6.5. Therefore, the time taken for grid cutting in this case is approximately 6.5 times time taken for cutting the contour. Thus, we see that we are devoting a far larger quantum of time to the undesirable material or the undesirable region in each sheet than the desirable region. The next question, question 7. What are the advantages of Kira's paper lamination technology when compared with cubic technologies, laminated object manufacturing? Does it offer higher strength? Does it negate any distortion or curling? Does it Is it safe from fire hazard? And does it have minimal internal strains? So we saw how in laminated object manufacturing, the strength of the bonded part was comparable to wood, whereas in the case of Kira's paper lamination technology, the strength of the bonded part was around 25% higher than equivalent natural wood. So option A is correct. Again, we saw that because of the use of a hot plate or a hot iron, there was minimum distortion or curling, which might be associated with the hot roller, which can have uh, shear stresses or slippage at the interface. So option B is also true. Again, since Kira's paper lamination technology uses a knife, a mechanical knife, instead of a laser, and because the temperatures achieved are lower than that in LOM, the fire hazard is also minimized. And because the iron, after coming in contact with the sheet, moves away, and then the sheet is allowed to relax and release these strains, the residual stresses and strains or the internal strains are also at a minimum. Thus, in this case, we find that all the four options are correct. In question 8, what is the primary disadvantage of sheet additive manufacturing process compared to other AM processes? Is it the lack of adaptive slicing? Is it the lack of materials library that can be processed? Is it the higher energy requirements? Or is it the greater hazard to health and human safety? The lack of adaptive slicing is something that we have reiterated time and again while discussing all of the sheet-based AM processes, and we saw that how because of the fixed uh, thickness of the feedstock, we cannot really have adaptive slicing. So whether the contour to be sliced or the build part or the part of the actual 3D CAD model is geometrically complex or relatively simple, like a rectilinear part, you will have to stick with a sheet of the same dimension. So if we have a sheet of lower thickness in order to achieve better uh, geometric control, we will have to have longer build times because now we'll require a larger number of sheets or layers of sheet to build the same material or to minimize build time. If we opt for a thicker sheet of material, now we'll not be able to capture the geometric nuances in a region with high curvatures. Thus, we cannot really have adaptive slicing. Or okay, in fact, this is what is a primary disadvantage? Is it the lack of materials library that can be processed? We saw how sheet additive manufacturing processes can be used for manufacturing paper, metal, ceramic sheet, plastic, or other similar materials which are available in sheet form. In fact, they can also be used to combine these parts into a multi-material part or these materials into a multi-material part, even for material combinations which might otherwise be metallurgically incompatible or which might lead to the formation of deleterious secondary phases. Thus, the lack of materials library is very untrue. In fact, it is one of the processes which is very versatile in terms of the materials that can be processed. Is it the energy requirement? We saw from the ASTM classification how ultrasonication, ultrasonic consolidation and other laminated object manufacturing processes fall on the lower end of the ASTM characterization or categorization. In fact, it uses only 5% of the energy in traditional welding process, for instance. Thus, the energy requirements are indeed on the lower side. Again, we saw that in most cases, there will be very low fumes, or while in some cases there is a fire hazard, it is still free from other hazards such as powder handling, um, such as the molten handling of molten material, and so on. Thus, it is very safe, and for some cases which do not use laser or use only a mechanical knife and glue, can also be very suitable for an office-like environment. Whereas for others, such as laminated object manufacturing, you will require proper ventilation to take away the fumes. So option A is the only suitable option for this question. And that brings us to the end of this live session. Thank you very much for tuning in. We have hit the halfway mark at week 6. This course is spread over 12 weeks. So I look forward to seeing you again next week. Thank you very much.